Hello everyone, this is Dr. Rahul Haware from the channel Ask Applying Scientific Knowledge. I welcome you in this 7th video of Rheology. If you guys have missed our previous video on this topic, I'm giving you the link of those videos in the description box below. So please do check that to get a continuity of the topic. Today we are going to evaluate the impact of temperature on the viscosity and of course on the viscosity of Newtonian liquid, as you can see the portrait of Sir Isaac Newton. So let's start with that one. So what is the general rule of the viscosity of Newtonian liquid? Well, the viscosity of a Newtonian liquid decreases. It decreases sharply with increase in temperature. So that's very important. So if you want to decrease the viscosity of the Newtonian liquid, what you have to do? You have to increase the temperature. And how can we model that? Well, we can model that with a powerful weapon which we are using in several concepts, and that is called as Arrhenius equation. And this equation is extremely useful in various topics of our physical pharmacy, like stability. Then you will be using that in the solubility, and again we are using here in the viscosity. As you can see, we have eta equal to A, and then we have one exponent which is raised to the power of EV divided by RT. And now this is an exponential function, isn't it? This is an exponential function. Why it is exponential function? Because we have this exponent. Now, in order to convert that exponential function into linear function, what we have to do? We have to take a logarithm. Okay, so let's take a logarithm of both sides. So ln eta is equal to ln A plus ln E, which is raised to power of EV divided by RT. And now here one of the rule of logarithm comes in picture. What is that rule? Well, the rule is log A of B is equal to, you can write B times log A. So we can do that here. Ln eta is equal to ln A plus EV divided by RT times ln E. But what is ln E? Well, it is an exponent, isn't it? Natural logarithm of exponent. And you can write something like this. Exponent has been raised to power of 0. And anything raised to power of 0 is equal to 1. Let's plug that value of 1, or ln E is equal to 1 in this equation. So what will be that equation becomes? Ln eta is equal to ln A plus EV divided by RT. I can just reshuffle this equation again. Let me make some space here. Or I can use here ln eta is equal to EV times R. I'm just rearranging plus ln A. And why am I rearranging this? Because I got linear function. And what is that linear function? Y is equal to mx plus c. So what is y? Ln eta. M is EV divided by R. X is 1 divided by t. And ln A, c is y intercept, and that is ln A. So when you are plotting ln eta as a function of 1 divided by t, you are getting some y intercept, and that y intercept is ln A. And from the slope you are getting EV divided by R. Okay, so let me rub out that because I got really nice animation on that one. So as you can see here, this is the linear function now. Ln eta is equal to ln A, which is a y intercept, plus ln E, EV divided by RT. And what is n? And then I was writing, if you remember previously, I was writing something like this, isn't it? And I explained that one. EV divided by R 1 by T plus ln A. Eta is the absolute viscosity A is the constant. EV is the activation energy, calories per mole, amount of energy required to initiate the flow of molecules. R is the universal gas constant, 1.987 calories per mole, Kelvin. And temperature is in Kelvin. So please keep in mind, temperature is always in Kelvin. And there is no degree Kelvin, by the way, like degree Celsius, degree Fahrenheit. No, it's just Kelvin. And why temperature has been always reported in Kelvin in such type of studies? Well, I will be making another video on that one, so please do check that video. So this is what I was talking. We are plotting ln eta as a function of 1 divided by t, and that's what we are saying in this general rule, isn't it? The eta has inversely proportional relationship with the temperature, and from the slope, this is the y-intercept, we get ln A, and from the slope you will be getting EV divided by R, activation energy. And what is the activation energy here? The amount of energy which you require to initiate the flow. And R is the universal gas constant, and by the grace of God you will be getting the value of R in the exam. So if we understand this concept, let's apply this concept. So now it's time to use what we learned, the Arrhenius equation, to model the relationship between viscosity and temperature. And we are applying that knowledge now to solve this problem. And what is this problem? The viscosity of human plasma at 37 degrees Celsius is 1.2 CPS. Assuming that plasma behave as a Newtonian fluid, that's important. Determine the viscosity of plasma required for an infusion which is kept at 25 degrees Celsius. And we have given the activation energy of plasma 4.25 into 10 raised to 3 calories per mole. And what is the activation energy? Well, that much amount of energy you require to flow the plasma. And these two hints are given. First, we need to determine A value using parameter at 37 degrees Celsius, and then use that calculated A to determine viscosity at 25 degrees Celsius. So generally what I do, I always figure it out what is given. So what is given? Eta is given 1.2 CPS, and that respect to temperature is given 37 degrees Celsius. I need to convert that into Fahrenheit, 273.15, which is equal to 310.15 Kelvin. Then activation energy is given 4.25 times 10 raised to 3 calories per mole. Then value of R is given by the grace of God 1.987 calories per mole times Kelvin. And another temperature is given 25 degrees Celsius. Again, please add 273.15 because you need to convert everything into Kelvin. And what is that? It will be 298.15 Kelvin. Now we know the equation, Arrhenius equation, linear form. What is that? ln eta is equal to EV divided by R into 1 divided by T plus ln A. And we have to figure it out what is ln A. So ln 1.2 CPS is equal to 4.25 times 10 raised to 3 calories per mole divided by 1.987 calories mole times Kelvin times 310.15 Kelvin plus ln A, and that's what we have to find out. So let's take care of first all these units. So calories gone, this mole will be gone, and this K will be gone, Kelvin. So this number becomes unitless, isn't it? So what is remaining now? ln 1.2 CPS is equal to 4.25 into 10 raised to 3 divided by 1.987 times 310 times dot 15 plus ln A. Let's go to next page. We have a lot of space here. So what was the equation ln 1.2 is equal to ln A plus 4.25 into 10 raised to 3 divided by 310.15 into 1.987. It becomes unitless, isn't it? So if we take the value of ln 1.8 is 0.1823 CPS is equal to ln A, and if you calculate this one, it will be 6.8963, and this is a unitless number, isn't it? And then I'm just ln A is equal to 0.1823 CPS minus 6.8963. So what is the ln A? It will be minus 6.7140 CPS. Please remember, this guy becomes unitless and only unit remains is from this guy, CPS, that's from viscosity. So now we got ln. So now we know the value of ln A, isn't it? And what is the value of ln A? Minus 6.7140. And now we have to calculate the viscosity at 25 degrees Celsius. So let's repeat that. ln eta is equal to EV divided by R times 1 divided by T plus ln A. We know the value of ln A now, isn't it? And we have to calculate the value of ln eta. So EV, we know the value of EV, 4.25 times 10 raised to 3 divided by 1.987 times, what is the 25? It's, when we are converting into Kelvin, it will be 298.15 Kelvin. So 298.15 minus 6.7140. And please keep in mind, this number is unitless, isn't it? And only unit is remaining, it's this one, minus 6.71407. So what value we got here? Well, if you calculate this one, it will be 7.1739 minus 6.7140 CPS, and that is equal to ln eta, which is equal to 0.4599 CPS. ln eta is equal to, and so eta is equal to exponent of 0.4599, and that's of course CPS. So what is the value of n25, or sorry, eta 25 is equal to 1.5839 CPS. And if you remember, N37 was 1.2 CPS and N25 is 1.5839 CPS. So what does that mean? Well, it means that when you are decreasing the temperature, you are increasing the viscosity. And that's true, isn't it? So I hope you got the clarification of the concept of how you can model the data with Arrhenius equation for Newtonian liquids. And on that note, I will stop this video, and I hope you have enjoyed this video. If you have enjoyed this video, please consider subscribing our channel Ask Applying Scientific Knowledge and share with your friends. So stay safe and stay curious. See you in the next video.